Hello, every EC members. Hello, everyone. I'm really happy to have this chance to share our project with all of you, especially for our FYP project. I think all of you are very interested in enjoying EC family and also interested in those kind of areas, including nowadays the hot topics are the artificial intelligence, using some machine learning to do some cool things, and and some other interesting topics, maybe for the computer science, do the coding and try to be a developer and making the software and also hardware together to make a uh, sophisticated project in your career in the future. So today I would like to share our final year project. Uh, and it is mainly focusing on the algorithm design and is mostly applying to the signal processing areas in which many of us, and I think all of you can also have the chance to take the signal processing course. And at here, we are going to propose our project at here. So it is about an algorithm designed in Engineering 8, and the applications are mostly related to the compensations of the hearing loss. But our special point, we are going to do some multi-channel manipulations. We want to do the multi-band and also have the wavelet-based methods and try to do it in the real-time manner, make our algorithm run in the hearing aids in the market, especially. So I'm today's speaker. I'm Jackie Lee Chen Ho, and our supervisor is Professor Kevin Child. And I'm now to credit my partners, Jason. He did a couple of slides of this PowerPoint. So let's begin with the introductions. So first of all, for our final year project, which are mostly we want to help the elderly aged people. They have the hearing loss problem. Uh, they can't hear the sound properly in their daily life. So there are really a strong needs for us to deal with at this kind of problem. So we want to propose a hearing aid, but the hearing aid is not the conventional one, it's a special one. Why I would say that because we want to focus on some special symptoms. As here, we want to emphasize the sensorineural hearing loss symptoms. Um, more specifically, and the patients can't hear some high frequency sound, but they can hear the low frequency sound as usual. But when they hear some sound, they want to raise up the volume, but it suddenly turns to a very high volume, and they can't really figure out why the differences of the volume as that's more because they can't bear the sudden increase in the volume. So we want to deal with this kind of practical problem and make it in an engineering manner. So at here, we want to propose our method, which is the multi-band compensations. And we want to do it in the discrete wavelet transform and also with the dynamic range compressor. So we can go into more details. And it is our project plan, which is about the discrete wavelet transform. At here, we want to do it in the more specifically in an engineering project site. So you can first see from here, it is our full block diagram, which is in which the red blocks are mostly encapsulates our implementations into this kind of method. So you can see from our methodology, we have the DWT, as I just said. From here, we also have the dynamic range compressors, which is mainly focused on the multi-channel analysis, because you can think of, after that, we want to amplify the sound before we pass it to a so-called simulator to simulate that kind of sensorineural hearing loss. So we want to do some pre-amplifications process. We have the dynamic range compressor for us to better analyze the frequency band in a proper manner and try to amplify a specific frequency band sound. And we also have the inverse transform, as you can see from here, IDWT, and also, as I just said, we want to simulate the practical hearing loss, sensorineural hearing loss. And finally, we will pass it to an objective measurement, which is called the speech-to-text recognitions, which is provided by Google. And yeah, as I just said, it is a red box, which is encapsulates our main implementations. And we also want to achieve the target, which is an inverse function. So the inverse function, what is this? What exactly is that? It is actually an function we want to achieve, which means we want to fully recover the sound, which can hear by the age people. They originally have that problem, but they can finally hear the sound again, the original one. Yeah, so let's go into detail. So this one is about the discrete Wavelet transform, which is the common engineering methods. And I think some of you may took the course of the signal processing, uh, in which you can learn some Fourier transform, fast Fourier transform, those kind of engineering methods proposed by some teachers or lecturers. They usually talk about. And in this project, we propose another advanced transform method, which is called DWT, discrete Wavelet transform. We also use the inverse transform as one of our application in this project. And you can see from here, we specifically say we want to achieve the level 5 DWT, and it is basically runs recursively. We take in a DT signals XN, and finally it will output the subbands. The subband is actually the some frequency band. We want to make it cut into a small half. So we have six in total, six subbands. And as I just said, it is recursive algorithm, so that's why there are the also base case and also recursive case. And finally, it will hit the base case and give out two wavelet subbands. You can see from the left top diagram, you can see we have CD1, CD2, all the way to CD5, and also have the CA5. So it's basically representing the recursive operations doing the convolutions of the XN with the high pass and low pass filter. As you can see from here, the left one is the low pass filter, and the right one is the high pass filter. Is the finite impulse response filters, FIR filters, and we also do the downsampling at the same time. And every levels, you can see, say for example, for level 3, you can see there are two versions of the signal coming out. One is representing the low resolution version, and another one is the high resolution version of the signals. And from the bottom, you can see the broad diagram, which is representing every subbands. They have their particular frequency band. You can see from the CA5, which is representing a relatively lower frequency band. You can think of those are for the sound lectures, which is the non-consonant sound. And so you can think of maybe the higher frequency sound, those are the consonants. Yeah, so we will also use the inverse transform IDWT to reconstruct the decomposed signals after just after our stage of the hearing loss simulator. We will go into details about it. So for the next part, which is about the dynamic range compressor for the hearing loss compensations, and the left half diagram, which is talking about exactly manipulations inside the compressor. We have 5 characterizations: first hold, compression ratio, attack time, release time, and also makeup gain. This is a more detailed diagram, which is talking about the compressor characterizations, and we can reach in the demo videos later, in which I will talk about more on that. And this one for the right portion, which is about the compression process, the more precise process into it. Basically, we have 3 stages. And first one, we have 2 signals in which the magnitudes are pretty far away from each other, which is one is a little bit small, another one is pretty high. And we try to fool this kind of dotted line, which is called chest threshold. And we want to compress the higher signals and keep the smaller signal at the same amplitude levels. And finally, we will do the enlargement of the signals in the amplitude. So you can finally see two signals, they have a small difference compared to the stage one. So you can see the red is representing strong signal and weaker signals. They are finally comes to the almost, I would say, almost the same amplitude level. So we want to make the small differences at the end. Right. So for the next part, we just talk about the how can we actually simulate the sensorineural hearing loss. As I just said, for the normal people, they can see from the first row of this spectrogram, you can see the sound are ranged from 0 all the way to 10,000. And after having the impact of the sensorineural hearing loss, the normal patients, they could only hear maybe say for example 0 to 1,000 hertz, those kind of sound. And you can think of this really hurts their normal hearings. They can't really hear some consonant sounds in their daily lives. So you would make their life even harder. Yeah. And the speech to text recognitions, which is proposed by Google, and we want to try to use this kind of service to verify our program results. Yeah. So it can show the accuracy of the through the comparing the original speech with our speech under the hearing loss simulator. Yeah. And we can compare the accuracy later. Yeah, so this one is our Google speech to text recognitions. These are covering some results we made. And this part is done by me, and which is about the speech enhancement part. And we take in different kinds of speech signals. They are clean speech and also noisy speech. We also cover 4 genders, and also different language. You can see from here, we have English, Chinese, French, and the hearing loss are covering from 125 all the way to 8,000 hertz, and they are in different degrees of the hearing loss. And the accuracy are mostly about also over 80% or above. Yeah, and we also think that, oh, this one is pretty nice and is really wonderful because we almost recover 80% or above for the signal part that's under the sensorineural hearing loss. And for the noisy speech, it's also done pretty well. And we also will talk about the music applications later, which is our extension of this project. Right, so come to our result showing part, which is about the clean speech, make it into the female English part. Yeah, so this one is our parameter settings, which is about 6 wavelet subbands, how would be the value of the subband values. So you can see from here actually for the CD1, which is having a relatively higher amplitude because we want to cover more high frequency sounds under our algorithm. Yeah, so we want to make, we usually want to make these kind of values as high as possible. Yeah. So this one is the original speech of the female English hearing speech. Let's take a look into it.
Introducing yourself to a crowd of people, or even just one person, can make anyone nervous. Doing it in a foreign language, even more so. So today we're going to go over a few phrases that you might say when introducing yourself.
Right, so this one is the original speech. It represents the normal people, they can hear this kind of sound. But if we under the sensorineural hearing loss, which is without our hearing aid algorithm, how the sound will be looking like this one.
Introducing yourself to a crowd of people, or even just one person, can make anyone nervous. Doing it in a foreign language, even more so. So today we're going to go over a few phrases that you might say when introducing yourself.
Right, so you can see from the spectrogram without speaking, the high frequency components are almost disappeared. You can see almost no components are, say for example, over 5,000 or above, there are almost no any high energy components. And please also note that actually the brighter the color, the more the energy. So basically this kind of spectrogram is representing the energy levels, and brighter the color representing more energy. So you can see no energy densities about 5,000. So this one is under our enhancement.
Introducing yourself to a crowd of people or even just one person can make anyone nervous. Doing it in a foreign language, even more so. So today we're going to go over a few phrases that you might say when introducing yourself.
Right, so up to here you can hear it more in the content of the message. In terms of the consonant sounds, you can hear some sound, add sound. And from the spectrogram, more details are shown from here and more energies are shown at here as well, which is consistent with our assumptions. We want to do some manipulation in recovery rate the signal. Yeah. Okay, let's take into the second signal, which is about the male Chinese screen speech.
我知道一家最近的咖啡店，离这里大约10分钟路程。你先直走，到达前面的公交车站后，乘坐123路公交汽车。过了2站之后，下车右手边就是那家咖啡店了。
Now this one is spoken by another Chinese guy, which is a male. Yeah. And we want to compare it, how will be the situation different from the female, and also is made in the Chinese version, so we can see from the parameter settings how would be the situation vary.
我知道一家最近的咖啡店，离这里大约10分钟路程。你先直走，到达前面的公交车站后，乘坐123路公交汽车。过了2站之后，下车右手边就是那家咖啡店了。
Right, so this also come to the similar situation, no high frequency components as said before.
我知道一家最近的咖啡店，离这里大约10分钟路程。你先直走，到达前面的公交车站后，乘坐123路公交汽车。过了2站之后，下车右手边就是那家咖啡店了。
Right, from here you can hear more details also in terms of the consonant sound, and yeah, you can think of a more clear pictures in terms of the high frequency sounds. Yeah. So this one is the noisy speech, which is the male English version.
I know a professional speaker. He's paid $10,000 an hour to speak. It's a good gig. He gets very nervous. He's up in front of crowds of thousands. Behind the stage, what he does is 100 push-ups right before he comes out. You can't be that physically active and not be in the present moment. Now, I'm not recommending all of us go to that level of exertion because he starts out of breath and sweaty.
Right, this one is actually involving the musical interference inside speech, so you can hear musical background noise together with the male speaking, yeah, at the same time.
I know a professional speaker. He's paid $10,000 an hour to speak. It's a good gig. He gets very nervous. He's up in front of crowds of thousands. Behind the stage, what he does is 100 push-ups right before he comes out. You can't be that physically active and not be in the present moment. Now, I'm not recommending all of us go to that level of exertion because he starts out of breath and sweaty.
Right, this one I want to mention at one point is this program is pretty different from the clean speech because we want to get involved in another speech into our program. So which involving the additions of signals, and you can So this one is pretty different, and the one just now is having no an enhanced versions without our hearing aid. Yeah, this one, the one I'm going to pay is having the speech enhancement.
I know a professional speaker. He's paid $10,000 an hour to speak. It's a good gig. He gets very nervous. He's up in front of crowds of thousands. Behind the stage, what he does is 100 push-ups right before he comes out. You can't be that physically active and not be in the present moment. Now, I'm not recommending all of us go to that level of exertion because he starts out of breath and sweaty.
So this one is having the constant sounds you can see from the audio track, and also they're involving some high frequency components. You can see from the spectrogram there are more details in the patterns. Yeah, so we can also did some speech recovery for the noisy speech. So for the next part, which is about the music results, we also have the extensions to it, and we basically Jason had made two sets of the hearing loss conditions for the speech enhancement results, and basically the overall results are enhanced for the left side, and for the right side, which is about the Google survey, is also done pretty well in the serious manners in terms of the high hearing loss. Yeah, we tested in the Mozart music, and the performance are pretty satisfactory. And so this one is for the demonstration of the classical music. This one is the original soundtrack for the Mozart music, which is the version will be heard by the normal people having no hearing loss symptoms. And the second one, which I'm going to play, is the enhanced version having the hearing loss problem. Right, so this one is for the situation having the hearing loss symptoms, and is also basically the same settings as the previous speech testing. And this one is the enhanced version. Right, this one is we can heard many high frequency components. Those are recovered above the 5,000 hertz. Those high energy components are recovered in terms of these frequency bands. So to conclude, basically we have achieved a real-time implementable multi-band and wavelet-based algorithm, which is having the function to compensate the hearing loss symptoms for the aged people, and the speech enhancement results are pretty great. And basically we can also work in several categories of the speech, and not restrict to the speech, but also recover for the musical audio. For the clean speech, we covered all genders, different language, English, Chinese, and also French. For the noisy speech, we get involved into musical interference, the bubble interference, and so on. And for the extension of music, we covered the classical music, as I just said, and we also have the bass, the vocal music. And finally, we want to how the aged people in overcoming the hearing loss problem in daily life, especially for them to hear the high frequency component sounds and get engaged in the society. And we also agree that it is commercially valuable in the hearing aid market in the future. So we also can get a sponsorship and launch our algorithm to have an exactly inverse function into the hearing aid market. The future work, we can also cover more settings, more testing and settings on the clean and noisy speeches, which is spoken by different speakers. They may be coming from different countries, and maybe multiple language. They can have their own dialects, and we also can cover different kinds of music. For the design part, for the compressor testing modules, we can also apply the PID controls so that we can make it less fluctuates in the performance. We can better control and so as to getting more close to the inverse function. Right, so yeah, so that's all for the brief instructions for our project. If you have any questions, you can contact me directly or ECE department. So for the next portions, I will directly show how we can test it in our program and how will be the real implementations of our final year project. So basically, this is the platform we are using in this final year project. You can see we are using the Visual Studio Code. And try to run the code. I have already copied the final path, so just paste it into the encoder prompt. Python. Right, so for example, we want to test the introduce yourself female, which is the female English version I just set from here. This one, the first example, the female English key speech. So I run audio tab, audio testing. Yeah. Audio testing. Use yourself, yeah. So yeah, just run it. Oh, they got into some problem. Let's fix it. Right, this one is saying that you try it again. Give me a second, I'm going to fix the problem. Right, so I think it's getting the normal situation as I just changing settings. Yeah, so the one I'm going to play is for the introduce yourself, the female English clean speech. Let's play it. We usually test it in this kind of command windows. As you can see, there are 6 compressors we are going to use in 6 subbands. The first 2 we are displaying is the original speech, and then the other one is the one just getting out from the discrete Wavelet transform. Yeah, so this is the results we have, for example. And then, okay, so after we have the results, we can go to another very important software we are going to test, which is called the Audacity. So just get into the previous file path. We have already get our result into this folder. We have 4 accuracy, so we have 4 audio folders from here. We can place it all together from here. So basically you can see different waveform. This software is very useful because we can also display both waveform and also having the spectrogram. Basically they are consistent because for the high frequency components, you can see they are exactly the same because the more high frequency sounds you can show from the spectrogram, you can see they're consistent from the plot from the waveform as well. Yeah, so this is mainly our usual conventional testing on our program. So for example, this one is the one having the hearing loss symptoms, and under our hearing algorithm, let's heard any differences.
Introducing yourself to a crowd of people, or even just one person, can make anyone nervous. Doing it in a foreign language, even more so. So today we're going to go over a few phrases that you might say when introducing yourself.
Right, and the one which is before our enhancement, how will be the sound looking like? This one, solo. Every time we just press solo because we want to play the dedicated soundtrack for checking any difference.
Introducing yourself to a crowd of people, or even just one person, can make anyone nervous. Doing it in a foreign language, even more so. So today we're going to go over a few phrases that you might say when introducing yourself.
Right, so from here we can heard also there are no any consonant sound. This is the before version. This one is the after version.
Introducing yourself to a crowd of people, or even just one person, can make anyone nervous. Doing it in a foreign language, even more so. So today we're going to go over a few phrases that you might say when introducing yourself.
So this one is the after versions. Yeah, and basically we have done the demo here, and yeah, and thank you very much. This is the end of our demo. Thank you.